Good morning, good afternoon, or good evening. My name is Adriana Tran. My group and I are mechanical engineering majors, and we worked on the static equilibrium problem. The problem states that there are two cables connected to two anchor points labeled A and C in static equilibrium with their respective tension forces, tension AB and tension BC. There is a distance labeled D between the two anchor points that is measured in feet, and the cables are holding a block with a weight of W, which is measured in newtons. There are also two angles, theta and phi, that are made between the two cables and the ceiling. We were tasked to create a data file of test cases that contain D in column 1, W in column 2, and length BC in column 3. With this information, we are to solve for an output angle theta and both of the tensions through MATLAB. Before doing so, we have to check the data within the file. The first check is to make sure that every value is positive. If there's a negative number within the data file, the code should replace it with its absolute value. The next check is to make sure that all values for length AB are less than the D value associated with it. If length of AB is greater than D, then the code should ask the user to provide a different value. After these two checks, we were to create a function that requires the inputs of D, LAB, and W that will output theta in both tensions. Then lastly, we were to plot the tensions with respect to length BC and then solve for the maximum length of BC. These are the equations we use to solve this problem. Since the object is at equilibrium, then the forces are balanced. That means the summation of forces in the x direction and the y direction is 0, and acceleration equals 0. We also use basic trigonometric equations to solve for the lengths and angles, i.e. SOHCAHTOA. This problem is a good demonstration of what mechanical engineers deal with on a regular basis. They would calculate the tension forces in the cables so they could design a lift system that will safely lift a heavy object and transport it from one point to another. Or they would determine the heaviest load that a crane in a factory can safely lift. Here is our code. We imported our data file of test cases using the function xlsread. We used the size function to assign the dimensions of the data file into the Excel sheet. The first block of code of nested for loops is to check if each value is positive. If not, a warning will be issued that the length cannot be negative and informs the user that the code will change it to its absolute value. It also terminates the program if one of the lengths is 0, because that would be impossible. The next block of nested for loops is to check if the length of AB is less than D. If the length is greater than D, the code will prompt the user to enter a different value, and it will continue to do so until the value is less than D. Here is where we call on our function staticfun, where it takes D, length of AB, and X. X is a segment of D. When me and my group members were solving this problem, we split the diagram into two triangles and solved for the angles and lengths this way. We just thought this way would be easier. And then we also input W into the function, and then the function outputs the angle theta and tensions AB and tension BC. In the function, we use the trigonometric equations SOHCAHTOA and manipulated these equations to find the variables we needed to solve for. At this part of our code, this last part, it was to graph the tensions versus length of BC, and we also put the appropriate labels on the x-axis and the y-axis and whatnot. Before I run the code, here are the test cases that my group and I created. As you can see, we included a negative value in the second row to test the first block of code to where it is supposed to replace the value with its absolute value. We also included a value of length AB that is greater than its associated D in the last row of our data file to test whether or not the code will catch it and ask the user to input a different value that is less than D. So when I run the code correctly analyzes the data, issuing a warning to the user stating that the length of either legs cannot be negative, and replace that negative value with its absolute value. Then the code continues to run and detects that the length of AB is greater than D and prompts the user to enter a replacement value. It continues to ask until the user inputs the appropriate value of length AB until it satisfies the condition that the value is less than D, as demonstrated. After the data checks, the code continues and the values are used in the static fun function to calculate angle theta and the two tensions. The code then brings up a graph with tension AB being the red stars and tension BC being the blue circles plotted. The X and Y labels are appropriately labeled, as well as the title. You can also see in the workspace that the max length of BC is 30.8869 feet and that angle theta equals 0.7227. An engineering student can tweak the test cases and solve other statics problems that are formatted similarly to this one. An engineering professional can also use this code for the same reasons, or even for a real engineering issue, such as anchoring a heavy object to the ceiling with two cables. However, this code is severely limited to solving only this type of problem where there are two cables and one object connected to those two cables. It cannot be used for a different type of static equilibrium problem with multiple cables or multiple objects. This concludes my video. I hope you enjoyed it.